Okay, so let's start. So it's a great pleasure to introduce Mengdi Wang. She is one of the rising young stars in reinforcement learning. So I'll quickly tell you her background. She did her PhD with Dimitri Butsakas in MIT and is now with Princeton University. I believe also has some affiliation with DeepMind. She has already garnered quite a few honors like Young Researcher Prize in Continuous Optimization, which is given only once in 3 years. Then Princeton ACAS Innovation Award, Google Faculty Award, and the MIT Tech Review 35 under 35 Award for the China region. So today she will talk about some theoretical results on model-based reinforcement learning. So before I hand over to you, Mengdi, do you want to break occasionally for questions or should I interrupt you? People will put questions on chat.
Feel free to interrupt me. Yeah.
Okay, thanks. So over to you now. You can start.
Excuse me, madam. Can you hear me? Hello.
Yes.
Madam, can you make a full screen? There is a play button. Is there? Yes. Just
Yeah, that doesn't work. Whenever I do that, my PC would somehow end up with problems.
Okay.
Yeah, I just try to minimize the sidebar as much as I can. Oh, that works.
No, just play the play icon.
No, that doesn't work. My Zoom will just fail if I do that. Yeah.
Okay. Okay.
Yeah. Let me make it as like this.
Okay.
Shall I wait or shall I start?
You can start.
Okay. All right. So thank you very much for the kind invitation. So it's wait. Okay. Okay, so it's my pleasure to present works on theoretical reinforcement learning in the applied probability society. So, so I'm with Princeton University, and also I have a partial affiliation with Google DeepMind. So we work on. So our focus of research is to understand theoretically what's the sample efficiency of reinforcement learning and how to design optimal algorithms for learning in a real environment. Okay, so I want to share some recent theoretical results with you guys. Wait. Okay, somehow. Okay, so the very basic mathematical model for reinforcement learning is very common. So it is the Markov decision process. So I think everyone has known this mathematical optimization problem from early literatures in operations research and in applied probability. So Markov decision process is a very basic model for sequential decision making with stochasticity. Okay, so in the very, very basic MDP model, usually, let's begin with saying that we have a finite number of possible states, and we have a finite number of possible actions to choose at each possible state. Okay, and so at each state, upon choosing some action, we have a reward function. We have a reward. So rewards this little r. I don't know if you can see my cursor. So this little r is a function of state and actions. And let's assume for simplicity that this r value is always between 0 and 1. Okay. And the Markov decision process has its own law of transition, which is a collection of transition probabilities. So from each state and action, there is a distribution of the next state. Okay, so the optimization problem is we want to find an optimal policy, which is a mapping from the state space to the space of actions. And we want to maximize the value of the policy, which is the expectation of cumulative returns to be collected on the random path generated by this Markov decision process. Okay, so this is the very basic model for reinforcement learning. Okay, so if we know the rewards We know all the reward values, and we know all the transition probabilities. Once we know that, this becomes an optimization problem, right? Then we can solve it in many different ways. We can do value iteration. We can do Q-learning, which is a stochastic approximation iteration. Where we can even formulate this as a linear program and solve it directly. Okay, so notice that I have a word tabular here. So tabular is really a jargon in the reinforcement learning community. So by tabular, usually we imply that we're working with discrete state space and discrete action space. And also, we do not have any additional assumption beyond this Markov decision process. Okay, so tabular means that we have no other structural knowledge. Okay, so first, let's review what do we know about tabular MDP, so which is the finite state, finite action, the simplest case. Okay, so we pose this as a learning problem. Consider a simple setting in which we have a generative model. This is again a reinforcement learning jargon, which means a simulator. Okay, let's say that we have a generative model or a simulator, so that from any given state and action pair, we can generate a random sample of the next state. So this generative model can replace the transition probabilities. So we can estimate the optimal policy without knowing the transition probabilities, as long as we have a generative model. Okay, and in this case, so the sample complexity for solving tabular MDP is already known. So I think we start with the lower bound. So there is this information theoretical limit proved by a bunch of DeepMind folks a few years ago, showing that if we want to find an absolute optimal policy, no matter what we do, we are going to need the following sample size. And the sample size depends linearly on the number of states times the number of actions. Okay, it also depends as a cubic function of the discount factor. Okay, so in the recent couple of years, so we actually were able to close the gap between upper and lower bounds. So we were able to actually develop the sampling-based algorithm that can achieve the information theoretical limit for the first time. Okay, so actually there exists now more than one algorithm to guarantee finding a near optimal policy with high probability within a sample size that is super close to the theoretical lower bound. Okay, and on another related notion for sample efficiency is regret. Regret means that I have to learn to make decisions on the fly, and we care about the cumulative errors, which is the regret we make during the online learning process. And in this case, there exists lower bound that again depends on the square root of number of states times number of actions. Okay, so I'm showing you these results because they are the very basic results for the finite state, finite action tabular problem. Okay, so hopefully this gives you a sense on how the dimension S and A play their roles in the sample complexity and regret for reinforcement learning. Okay, so I want to talk about model-based reinforcement learning. So what this means? So this is a figure I stole from the famous Sutton Bartle book on RL. So this is the diagram of model-based RL. And if some people in the audience come from control, you might tell me that this is not RL, this is really just model predictive control. So model-based reinforcement learning is in some way pretty close to model predictive control. So what happens is the overall learning process is going to be iteratively collecting experience by acting in the real world. And the agent, after collecting experiences, is going to somehow fit a model. And after fitting a model to the experiences, the agent will make decisions. So he's going to do planning using the learned model. And so he's going to compute value functions or policy functions for the next data collection period using the learned model. And then he's going to collect data again. Okay? And more precisely, we mean that we want to fit a model. So this model can be as general as the collection of transition probabilities for a Markov decision process. Okay? So in the tabular case, the model is going to be the collection of all the probabilities. So we fit a model to experiences. So our experiences is going to be the state action transition trajectories that have been collected in the during the course of online reinforcement learning. Okay. And then we care about, okay, how do we fit a model? And can we come up with regret guarantee? Okay. And now, since that we're calling with, now that our focus is a model, right? So our model doesn't have to be as generic as a finite state, finite action MDP, because we do know that if we discretize the state space in a naive way, we're going to suffer the curse of dimensionality, right? So now by fitting a model, we actually allow a richer class of models for reinforcement learning beyond tabular Markov decision process. Okay, so next I want to give you some, I would say, toy examples to show you that how one can efficiently learn a model for this Markov decision process while acting in the real world with provable regret. Okay. So, and by the way, so rigorous definition of regret is the following. So say that we have a learning algorithm. Okay, right. So the regret, by definition, is the difference between the theoretical maximal value that could possibly be earned, which is this V star S0, optimal value from the initial state S0, okay? And the sum of actual returns collected on the trajectory, okay? And this definition applies to finite horizon episodical reinforcement learning, in which the agent plays the game episode by episode, and there are going to be n episodes, and each episode consists of h time steps or h individual decisions. Okay, so the regret is an overall a function of either n or t. Okay, so I do need to mention that there exists a lot of works, and actually I think there are many more papers coming out in the recent couple of years studying the regret of reinforcement learning using different algorithms under different assumptions. Okay, I just want to give you a sample of the result. Okay, so a generic framework for model-based reinforcement learning is known as upper confidence reinforcement learning. So in some ways, it can be viewed as as derived from upper confidence bandit algorithms. Okay. So now, what's different between RL and bandit is, so now when we construct a confidence set, we are always going to be construct a confidence set of the unknown transition model, and we construct such a confidence set based on experiences, based on the sample trajectories. Okay, and once we have this confidence set, we are going to do optimistic planning, meaning that we are going to look at all possible transition model P in the confidence set B. Okay, and we are going to be optimistic. We are going to choose the most optimistic policy pi that maximize the best value corresponding to the best instance in the confidence set. Okay, as you can see, this is actually in some way very similar to upper confidence bandit, except for that our objective is the value of a policy instead of the value of a single decision. Okay, so now let's try to make this more specific. First, let's consider a very basic set of systems. So what if we work with finite horizon deterministic transition system? Okay, so the reward is going to be deterministic, and the transition function f from state action to state is going to be a deterministic function. And now in the reinforcement learning world, we want to learn the optimal policy. Okay, so we want to solve this optimization problem, but we will not know the reward function little r, and we will not know the transition function f. We have to learn those unknowns by acting in the real world. Okay, but we're going to assume a little bit of structure knowledge. So suppose that the only knowledge we have is a metric, meaning that we have a measure of distance in the state action space. And our assumption is we work with the class of Lipschitz continuous transition models. Okay, so now you can see that, okay, we work with control systems that are deterministic. We do not know the transition functions, but we have the assumption that I have a known metric and the system is in some way continuous with respect to that metric. And my question is, how fast can we learn to optimally control such a system? So this is a simple example in which we actually don't have probability yet. Okay, and algorithm turns out to be very simple. It's I would say, a special case of the abstract upper confidence model-based RL algorithm. Okay, so we can write it in a way that mimics Q-learning. Okay, so say that we are at the beginning of a new episode, and we have stored all the data we have collected so far in a buffer. So let's call this buffer DN, stands for data after n episodes. Okay, so now we want to use the data we have to do Q iteration, or to solve the Bellman equation approximately. Okay, so since we don't really know the transition function, we're basically going to do a nearest neighbor Q-learning update. So we can do that easily because this is a deterministic system. We don't have to estimate expectations. So if I want to know the transition from this state, I would just look for some neighbor of this state and use the transition that we have observed at the neighbor as a proxy. Okay, but we are going to do a bit more than that. So we want to do optimistic upper confidence planning. So we're going to add a bonus term, which is this distance term on each possible neighbor, so that for each possible neighbor, we compute an upper bound for the Q update. And then we're going to take the sharpest upper bound from all possible neighbors, meaning that we're going to take mean over all data we have collected in the data buffer to get the sharpest upper bound for each Q value. So by iterating this process, which is really Q iteration with nearest neighbor search with a little bit of optimism, okay? So we can always compute the best Q values based on the current data, which allows us to choose actions in the next episode. And then we're going to iterate this process. Okay.
Mengdi, can I ask a couple of questions there?
Sure.
Yeah. One question is from Shalab. He says, is F known here?
F is not known.
Okay.
Yeah, thank you. So I had this f of s prime and a prime. So this particular transition is known because it is in the data buffer. Okay, so this overall f function is not known except for the state actions that we have visited. Okay, so we know a
Yes, sir.
few
Yeah,
points
sorry.
of this f, and we collect more data points as we go. Okay, great question.
There are a couple more now. The one is from Devavrat Dubashi. He said this seems similar in spirit to the hierarchical learning in Lipschitz bandits by Vivek et al.
I think so, but actually, I think this is much simpler than that.
Okay, another question from Alexandre Cloutier. What is the connection with Q learning with nearest neighbors by Shah and Z, NeurIPS 2018?
I think actually this paper came out earlier, and the assumptions are different. And also, this particular result I'm talking about has an explicit regret. And I think that newest paper, to my best knowledge, is more about sample complexity. So sample complexity and regret are very different notions, because in dealing with regret, we have to deal with dependent data, and we have to do optimism, and there are a bunch of things that we need to do. And if we simply try to think about Q learning with nearest neighbor as a stochastic approximation algorithm, then it's mostly about convergence and convergence rate. But in regret, you can see that the data collecting distribution is changing and is adaptive. And so the nature of the results are different. So if that's the paper I have in mind, I'm not exactly sure whether we're talking about the same paper, but probably the difference is one is about online learning, the other one is about learning with a simulator. Okay, thank you.
Yeah, thank you. I think that's all for the time.
Great, thank you. Okay, so what can be proved? So we can show that after K episode, that algorithm learns with a regret. And you can see this regret, well, depends on horizon, depends on this big D, which is diameter of the state space with respect to the known metric. It depends on Lipschitz constants. It depends on the number of episodes. And also it depends on this little d here, which is the doubling dimension of the state action joint space. Okay, so so first, such a regret doesn't appear to be a good regret, because we can see that as little d is large, this regret is close to linear. So this is actually a regret that actually suffers from the curse of dimensionality. Okay, but we can actually also prove a lower bound showing that this regret upper bound is minimax optimal, in the sense that if we work with continuous deterministic and Lipschitz continuous systems, and if we don't have other additional structural knowledge to begin with, we can't do better than this regret bound. Okay, and what's interesting is the notion of doubling dimension. So doubling dimension, well, which is really just the dimension. So it tells us what is the intrinsic dimension of a space once we are given a distance or a metric. But we want to know that doubling dimension is usually significantly smaller than the raw dimension of the data. Okay, for example, if we think about the states as raw pixel images of a video game, so those images, we can view them as lie on a smooth manifold, and this doubling dimension is going to be the intrinsic dimension of the manifold, but the raw dimension could be the number of pixels. Okay, so in some way, this algorithm is automatically learning the manifold at the same time when solving the optimal control, the dynamic programming problem. And it doesn't have to know the doubling dimension to begin with. It can adapt automatically to the underlying latent structure of the state space. Okay, so this is one illustration. So if we work with the class of continuous systems, then we can utilize this structural knowledge, build it in model-based RL, and we can get provably small regret. Okay, so now I'm going to change the gear. So now let's work with stochastic transition systems. Okay, so in RL, typically whenever we work with state and actions, we're going to featureize state and actions into some vector, some numeric vectors. Okay, so we can think about a feature vector of a state. We can view it approximately as, for example, the second to last layer embedding of a neural network. Okay, so suppose that we can vectorize states and state action pairs into vectors. Okay, and also we're going to suppose that the feature vectors we are given are sufficiently expressive so that we can embed the unknown transition kernel, this unknown P, into a lower dimensional space spanned by the feature vectors. So this is actually an assumption which implies that we can predict state-to-state transition using a linear model. So that's really what the assumption is. Okay, and it also basically saying that we can embed the unknown transition kernel into a finite matrix. Still a strong assumption, but it can be useful in actually a lot of occasions already. Okay, so under this assumption, we have feature map and we can embed unknown transition kernel into a matrix. Now we can do a model-based RL algorithm. We call it MatrixRL. And again, what we can do is very similar to bandit. And in this case, it's actually very similar to linear bandit. So we can construct a confidence ball around the estimated transition kernel. And then we use the confidence ball we have constructed to compute optimistic Q function values. Okay, so this is the key step. And then we choose actions according to the new Q value estimates. Okay, and in this case, one can show that we can actually get much tighter regret. Okay, so one can show that the regret now depends on root T, which is min-max optimal for sure. And also what's interesting is it depends linearly on the dimension D. So it depends linearly on the dimension of the feature map. So this regret is actually not entirely minimax optimal. The dependence on H horizon is not optimal, but other dependents are optimal. Okay, so it shows us one way to think about stochastic transition systems if we have good features and if we can somehow embed the unknown system dynamics into the feature space, then we can learn with provable regret that depends linearly on dimension of feature map. And this result can be generalized to reproducing kernel space. Okay, so now suppose that we don't have the feature map, but we have a kernel function to begin with. So I can measure the kernel similarity between any two state action pairs. Okay, and our generic assumption is that the transition kernel here, the transition kernel P, belongs to a product Hilbert space spanned by the kernels. And then we can actually translate that MatrixRL algorithm into a kernelized version. And in this case, we can show that the regret of learning a kernel transition systems depends on this. So again, it's a root T regret. And also it depends on the effective dimension of the kernel space. Okay, so the true dimension of a kernel space is infinite, but the effective dimension of a kernel space depends on the data, and it's usually something finite. And the regret also depends on the Hilbert space norm of the underlying transition kernel. Okay, so this is another toy example in which we can handle reinforcement learning when we know that the transition model can be expressed using good feature maps. Okay. So now I think the real meat I want to talk about is we want to be able to generalize from those specific model classes. So can we do something more generic? Can we learn a more generic model? And also, can we fit the generic model in a more generic way? So to talk about that, I want to bring your attention to a very recent advance of reinforcement learning by DeepMind. So MuZero. So we started working on this a while ago, but MuZero was recently accepted to Nature, I think in the past months, but the paper has been under review for a long time. So MuZero is the state-of-art deep RL algorithm, okay? So it is a single algorithm that can solve more than 60 games and then can beat the best player in each of the game. Okay, so why is this a surprising result? So we know that, for example, Go has been solved many times, right? DeepMind first proposed AlphaGo and then AlphaZero. But AlphaGo and AlphaZero are specific to two-person turn-based zero-sum game, okay? And so if you're familiar with the deep RL world, so there are going to be a bunch of algorithms on GitHub and on OpenAI, and some of the algorithms work on some of the problems. But to really make general AI possible, we actually hope to eventually have a single algorithm that can learn to solve games with different natures. And the MuZero is an important step towards this goal. Okay, so you can see that MuZero actually can solve all the Atari video games, and then can also solve chess, Shogi, and Go. So those games are of very different natures. Okay, so MuZero is a model-based RL algorithm. So it's general because it doesn't know the rules of the game to begin with. So it automatically learns the rule or learns the transition model of the game and the plan using the learned model. So it is a powerful algorithm because it is model-based. It tries to learn a model without knowing the model to begin with. Okay. And a very important feature of MuZero is it doesn't try to fit a model to predict useless quantities of the game. It only tries to predict quantities that are central to the game, which are values and policies. Okay, so actually, I think this is a subtle point that I want to bring to your attention. So in deep RL, whenever we do model-based RL, okay, the common practice is we try to fit a transition model. So whenever we are given a state action pair, we can predict the next state. Okay, so this is actually what we implicitly did in the previous two results. Okay, in the nearest neighbor one, I used the nearest neighbor to predict the next state. Okay, in the MatrixRL algorithm, we try to parameterize the transition kernel with a matrix, and that matrix can be used to fit the data and predict the next state. Okay, so state action to state prediction used to be the common practice for model-based RL, because that's what we do or what we fit in order to learn the model. But MuZero does something very different. Okay, MuZero does value-targeted regression. Okay, the difference is we don't try to predict the next state. I'm going to begin with the current state and action, and we have a current value estimate. Then we're going to fit the transition model to predict the next value. Okay, so that's the major difference. We try to use value as a target. We don't use state as the target. Okay, so why is this important? So because, for example, if we think about a video game, if I want to predict the next state can be an entire image, and most of the pixels of the image could be background, which are not related to the game. So if we try to learn to predict the entire image, we are going to need tons of data and a lot of training power and a lot of tuning to predict each image precisely. So that's going to be another sub problem, which is also hard. But if we have a value function and I want to simply predict the next values of the state, then we're going to be predicting one-dimensional variable. This is a much simpler model fitting task. It requires significantly less data and it generalizes much better, right? But the difficulty is we don't really know the value function. We want to learn the value function. Okay, so if we know the value function, we don't really need to learn the model, right? So can we learn the transition model while learning the value function? So that's the key question we ask, and that's what made MuZero successful. So now the assumption we have is we work with a general class of transition models. So we have this capital P, which is a general class. We know that the true transition model belongs to this class. So we know the transition class, but the transition class doesn't have to be a particular linear model, or it doesn't have to be a particular parameterized model. We can view it as a general class, or we can view it as a class of transition models that are expressible by a certain neural network architecture. Okay. So starting from this general transition model class, we're going to be building our confidence set. So we're still going to be building the confidence set by using what we know from regression. Okay. So for each possible transition model, this P prime is a possible candidate model. Okay. So we can compute its value prediction error. Okay. So say that my current value estimate is VT, right? So I know this value function and I know this transition model. Then from a given S and A, we can predict the value of next state, right? And in the real data, we observe the true next state. So we also observe the value of the true next state. Okay, so then we could construct the regression loss function. We simply are doing least square regression to fit our prediction to the observed value of next state. Okay, and then the confidence set is going to be a set of candidate models with small squared prediction error. That's very simple, just regression loss. Okay. And what's tricky is the value target VT is the value estimate of learned by our algorithm. So this VT is actually a changing target. Okay, so that's the subtlety here. And here is the full algorithm. So it's a little bit, I think my slide is too dense, but I just want to say that what's going on is, so say that my transition model is parameterized by theta, okay? Then the key of the algorithm is value targeted regression. We are really trying to fit the transition model or the parameter theta by doing least square regression and by constructing confidence set using least square regression loss. Okay, and then again, we do optimistic planning by picking the most optimistic policy corresponding to the confidence set of transition models. So what's really tricky here is when we do model fitting, we're doing value targeting regression, and the value target, this V hat here, is being updated as the algorithm runs. Okay, so the algorithm is actually doing two things. It's learning the optimal value using the policy planned using the learned model, but the learned model is learned using the adaptively changing values. Okay, so that's the tricky part. Okay, so what's really interesting is the proof somehow works out beautifully, even though the algorithm seems to be actually a little bit unexpected, intuitively speaking. Okay, so we can show that, okay, the regret of this algorithm, we call it upper confidence RL value targeted regression, VTR. So the VTR algorithm achieves a regret. And again, the regret depends square root on the number of episode K. And also it depends on square root of the eluded dimension of the model class, and also the log covering number of the model class. So they can be viewed as just two different notions of dimensions, okay, for the generic class of transition models. Okay, so this is actually a very strong result, because we can now say that you can give me a class of transition models, and if that's the structural knowledge we have, we can design a value target regression based RL algorithm to learn to find the optimal model and the optimal policy with regret depending on dimensions of the model class. Okay. So, to illustrate some special.
Mengdi, can we break for a few questions?
Actually, this is my last slide.
Oh, okay.
Okay. Yeah, I'll stop from here. So we can do some special cases. So for example, if my model class is a class of linearly parameterized model, okay, and say that I have a parameter theta of dimension d. In this case, the regret becomes just d times root t times root h cubic. And also, if the model class is this class of sparse linear transition models, then the dependence on d reduces to dependence on root ds. Okay, so one can try to specify this regret for other particular model classes. So those are two examples I think which will illustrate how the actual regret will look like when we have a specific model. So yeah, actually I do have more slides, but I don't think I can finish them. So I'm going to end here. Okay, so I talk about this part. Okay, so basically model-based RL, model learning and regression can be made efficient for online reinforcement learning. Okay, so we can handle linear models and nonlinear models. Depending on the structural knowledge we have, it's possible to design model-based RL with strong generality. So that's the end of my talk. Thank you very much.
Thank you.
Questions? Yeah.
Yeah, I'll just read out the questions in the chat box. So first is by Abhishek Gupta. He asks, is it natural to think of feature spaces of state or state action spaces will form Hilbert spaces? I think this is
yeah, that's a very good question. So basically, I wouldn't say, we cannot say that a state space is a Hilbert space, because Hilbert space is a space of functions. Okay, but we can think about transition function or Q functions or the transition operator to be preserving a Hilbert space. Okay, does that make sense? So in some way, this is really pretty similar to all the things we do in function approximation in machine learning, right? In machine learning, if I want to predict what y given x, and if we are doing kernel methods, essentially the assumption is the function, the conditional expectation of y given x belongs to a Hilbert space. Or if it doesn't belong to a Hilbert space, then we can also provide approximation guarantee. So I would say that the Hilbert space approximation, the Hilbert space assumption is really an assumption that guarantees exact function approximation using kernel methods. But to be as generous as possible, we can also do broader assumptions to allow me-specified kernel space. Thank you.
There's a question from Hemchandra. I think this is about your comment that you are learning the value function, and he asks, he says kernel methods do this ? So I guess the question is, don't kernel methods also do this?
Like which kernel methods? Well, I mean, that method is based on kernel method, right? Kernel methods are for, I mean, our method is one of kernel methods, yes. But ours was the first kernel method with provable regret for reinforcement learning.
The next question, yeah, sorry. Maybe Hemchandra, do you want to elaborate on your question?
No, I think whatever she mentioned, I think this is what I had in mind. This is fine.
Okay, thanks. So the next question, There are a couple of more questions. Then, sorry, you were saying something?
No, I just said that. Thanks. This is what I had in mind.
Okay.
Thank you.
So the next question is from Devavrat Dubashi. So do you need both types of dimensions in that bound, which is eluder and the covering number?
Mm-hmm. Yeah, that's a great question. So I think that dependence is tight. I would say at least for many model classes that we know, it might not be tight for every single model class. For example, in the sparse linear case, that two dimensions will give us a root ds dependence, and that root ds is actually a lower bound in sparse banded. So I would say in that case, I would say the eluder dimension is the dimension, characterize the dimension for exploration, but the log covering number characterize the dimension, I would say the learning dimension or the complexity of the object. So both of them are needed for sparse online banded. So I think that's a toy example for me to think about. So I think that dependence is sharp if we want to have a general result, but I think it could be improvable in some special cases.
The next question is by Pratik. Is all of these regret-based ideas and bounds are the same ideas from that of online convex optimization? That's the question.
Well, I would say like in reinforcement learning is very different because we are working with a transition function, and whenever we make a decision, the decision is going to impact the returns and observations in many follow-up steps. But in online optimization, the bandit is actually a very simple problem because whenever we make a decision, the decision will immediately generate a return, and that's it. And in the next round, we can have a fresh start. But in reinforcement learning, it's a control problem, right? It's like, for example, like when we search in a maze, if I make a wrong decision at the beginning, I might just lose the entire game, right? Does that make sense? So having this state transition system generates a lot of difficulty, and that's really why reinforcement learning is, I would say, is an independent area. It's not derived from online learning. Reinforcement learning is about how to learn to control, and control is a problem that's very different from just pure optimization. I would say like online optimization and optimization are very nice mathematical abstractions or simplifications, but control a complex nonlinear system or complex dynamics itself could be a harder problem. And learning to control is in some way different or harder than learning to optimize a simple function.
So the next question is from Satyam Verma. Metric-based UCRL seems similar in functioning as UCT by L. Coxis et al. With an additional information of existence of a metric. Is it so? Or are there any other major differences?
I would say upper confidence methods follow pretty much the same diagram. I showed the basic idea in the very early slide, but I'm not exactly sure what is UCT.
Hello, Mr. Satyam, can you respond to that?
Yeah. So basically, in the paper, they are applying upper confidence bounds.
You mean
in
Monte
the
Carlo
sort
tree
of,
search, right?
yeah, but in this paper by Alfoxis, they basically wanted to predict the Q values and state action values. So on the basic idea of Vanilla Monte Carlo, where they randomly sample any of the actions, they replace that by using this upper confidence bound on the Q values.
Mm-hmm.
And
Yeah, good.
that,
mm-hmm. Yeah, good. So I would say, I mean, there exists more than one upper confidence RL algorithms, and the upper confidence tree search is one of them for a particular tree search problem. So the MatrixRL algorithm is another one of upper confidence RL that applies to systems with a metric. Okay, but in reality, actually, there actually exists other earlier upper confidence RL algorithm even for the tabular case. So I wouldn't say like they are definitely related because they all follow the upper confidence basic idea. But how to utilize the structure, either the tree structure or the matrix structure or other linear structure, So, or hierarchical structure. So how to actually utilize that structure and build it in the abstract framework with proof of regret, I think that will require a case-by-case analysis. But I think the baseline idea of upper confidence learning is the same. And it comes from upper confidence bandit.
Thank you.
Thank you.
It looks like there are no other questions. So let's thank Mengdi for a fantastic talk. Let me clap on behalf of everybody.
Thank you very much.
I guess that's the end of today's session.
I think, yeah, it's worth mentioning to all the people from India that the next talk is at 9 a.m. tomorrow. So it's a little early in the morning. Hope you can make it. Devavrat, for you, it's going to be even more early.
I don't think I'm going to make it.
All right. Well, thank you, everyone.